All right, so let's go ahead and look at some of the information necessary to complete the module folder 3B pre-lab for ideal gas. Again, I've preloaded the simulation just to avoid any issues sometimes occurring with these loading slowly. Okay, then with this, what we want to think about, these multicolored dots are to simulate gas molecules that are bouncing around, bouncing off of each other, bouncing off the container, and a couple of things we want to think about. So as there's more space, then they're less likely to bump into each other and bump around the edges of the container, and so the pressure comes down. Also, if I make this much smaller, then you can see that now they're a lot more likely to bump into each other and bump into the container, and so the pressure goes higher. This was with a constant temperature, and so this is called an isotherm, which again is described down in the instructions. Now I can change the temperature in general, so let me make this big just so it's easier to tell the difference. But in general, with a lower temperature, you're going to have smaller movements with these, lower overall kinetic energy or motion between these. Now that's an average sort of number, so if you look carefully, occasionally you'll see one that's almost stopped, like that one, and then other ones will bump into it, share that energy, and move around. At a higher temperature, you're going to have a higher energy average for the molecules, and then, even higher we go here. Well, as they're going around faster, that makes them more likely to bump into each other, and so you can see that the pressure changes with temperature as well. So these are intrinsically related to each other. Then if we change all of these things at the same time, then you'll notice that, as I make this smaller again, we have a compounded effect. Now that I have a high temperature and a small space, these are jumping all over the right place with lots of energy, bouncing around, bouncing off of each other, bouncing off the container, and making overall high pressure. Then the opposite, if I make a really low temperature in a really big space, they have less energy and a lot more room. They are much less likely to bounce off of each other and bounce off the container, and then that's our minimum pressure. Okay, so let's work through some of these questions and see what we can answer from that. So very first thing we want to do, we want to set the temperature at 500 Kelvin. Okay, so that's done. We want to set the volume at 5 liters. I like to see the full isotherm if I can, so usually I'll drag that back and forth before I set on the actual requested volume. Okay, then determine the resulting pressure and basically find the matching answer choice. So there are a few different ways that we can calculate this, excuse me, or at least some of the future questions once we've seen how it started. But we can just read the pressure from here. So we get 100 kPa, technically should be probably a lowercase a, but kilopascals, thousands of pascals, that's the pressure we're going to use to measure these. Now this is some magical, nice, wonderful gas here where we can estimate the pressure by taking the temperature divided by the volume. That's not always going to work out, but it is the case for the thing that we're looking at here. Okay, so we've got that information. Let's go back and find the answer choice. Looks like for me it's letter C. Okay, so we want to see what's going to happen now. We're going to keep the same 500 Kelvin, and then we want to change the volume to 6 liters. Now, we talked about this a minute ago. If we're keeping the same temperature, and we give more space, then think about that. That's going to make the molecules less likely to bounce into each other. So it seems like that this is going to be our best choice. But let's look at it and see. You can also use the isotherm. We've got the curve for this, so technically I've already spoiled the answer. But let's adjust and look. We go to here. The pressure drops as there's more room. Again, we can also estimate 500 divided by 6 gives us 83.33 here. That's all seems to match what we expected. Okay, then question 3 is going to have us do basically the same thing, but take it in the opposite direction. So in this case, if I'm going to decrease the volume, I've got the isotherm here. Again, I could technically sketch out on the line and see where that's going to go. but let's just adjust it and see what it looks like. So now we have less space, same temperature, so it means same average, motion and energy, but there's a lot less space, and now they're a lot more likely to bounce off of each other and bounce off of the edges of the container. So it should hopefully make sense that the pressure is a lot higher. We really didn't have any choices we could have excluded this time. I suppose we knew it wasn't going to be the same, so it wasn't going to be 100 because it was 100 earlier. We just weren't sure how big it was going to go until we ran it through. Okay, and then we need to be really careful on the next one to make sure that we read and see exactly what it says to make sure we don't miss, a small word here or there and cause an issue. So constant temperature, well, we kept 500 Kelvin for all of these, so that's true. Which might make you lean towards choice D, but try not to fall for the little traps that are sometimes in these. So we want to see, if we could eliminate all three of the other choices, then we'd say temperature wasn't important, but I feel like it probably weighs in somewhere. Okay, so larger volume, higher pressure. Well, we can just check and see if that happened, right? So we can take the volume, bring it back up to 6, and notice that's the smallest pressure. On the graph, it's the lowest point here. So that seems to not be true. So it's not A. Smaller volume, lower pressure. Okay, so let's go the opposite way. Smaller, 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 and pressure is really big. So not that. The smaller volume causes a higher pressure. Well, that seems to be true, right? And again, intuitively, it should make sense because if there's a smaller volume, there's less space, they're going to bounce off of each other more. That's going to cause the pressure to go up. Okay, so let's move on to the next little group. So we're going to use 200 Kelvin for this next part, at least just for here. Again, I like to slide the volume back and forth to get the full curve. Then we're going to use 2 liters. So here, almost there we go. And determine the resulting pressure, record the answer. So, again, we've got our mystical, magical, colorful gas here that where we can estimate from temperature and volume and find pressure. 200 divided by 2 is 100. So, again, that's not going to work for everything, but it does work for our colorful dots here. We can also confirm that by reading from underneath here or looking at the graph that we seem to have 100 kilopascals. Okay, so now question 6 has us do something kind of interesting, right? It's not an option really with this setup to keep a constant pressure, but what we can do is we can change a value, and then we can change some other things to put the pressure back to what it used to be. So that's our sort of workaround for that. So we want to remember, and hopefully, you got this question right when you were following along or thinking it through. We want to keep the 100 kilopascals of pressure. Okay. Well, when this tells us to go to 4 liters, that means we're going to have excess space. So the molecules are less likely to bounce off of each other, then that pressure should go down. Let's see if that's what happens, right? So excess space, we're going to 4 liters. And sure enough, we've got less than 100 now. The question is what does the new temperature need to be in order to make the pressure the same number it was before, right? So we have some options. Right now we're on 200 Kelvin. So let's see, what do you think will happen if we go lower, right? Lower means less energy. And look, the pressure dropped. So that was for sure not it. So let's go higher, right? Let's go here. Oh, and obviously we went a bit too far, didn't we? Because we did make the pressure go up, but it didn't go up to 100. It went past 100. So that's not what we were looking for. 500 Kelvin, still too much. So maybe 300 Kelvin. Oh, nope, that's too little again. So 400 it is, right? If you think about it, that should really kind of have made sense because, well, 200 Kelvin and 2 liters, right? 200 over 2 gave us 100. And then so 400 over something, right? So 4, there we go, right? So technically, we can solve proportions with these. Our main setup, if we have pressure, volume, and temperature that we're looking at, then that's going to make some constant, some number. If we had a little more information, we could find exactly what that would be, and run through some stuff, find some missing information. But what we've got in this question, we have another sample of gas, or at least a change on the same sample of gas, and sort of a before and after, right? So at the first point, we'll put little red ones on that one. Then we had, a set pressure, volume, temperature. We had some numbers that were given to us. Then we're going to adjust some small pieces and see what's left over. All right, so let's think about what our instructions were. We had temperature and volume. Then we're given a new volume. We're looking for a change in temperature. We're trying to put the pressure back to what it was. So a little bit of reading between the lines here. But if we want the pressure to be back to its previous value, right? So even if you didn't remember what that pressure was from the previous question, if I want the pressure to go back to its previous value, well, that means that this pressure and this pressure are the same as each other, and we can cancel them out. For what's left over, we can make a proportion. That looks like this one. And then, you could also have used that method to go through and solve. It may technically have been faster if you were comfortable building proportions, but, honestly, it wasn't too bad to just look at the simulation and track the numbers. That may or may not be a hint for later. So, let's see. All right, let's record an actual answer before we get too far distracted. 400 Kelvin, right there. Okay, so let's see which of these things is true. So increase in volume requires an increase in temperature to keep the same pressure. Is that what we did? We went from 2 liters to 4 liters, and we went from 200 Kelvin to 400 Kelvin. And both of those had the same 100 kilopascals. Yeah, that seems to be what we did. If we look at the next one, just to make sure, increase in volume starts the same way, but here decrease in temperature. No, decrease in temperature. We tried that and it went the wrong way. Decrease in volume, increase in temperature. So notice that this is more or less the same as what we had for B, right? That these are moving opposite ways of each other, and it's just not what happened. The fact that we were able to make a proportion means they're directly related, so they're going to move in the same direction. If one part goes up, the other part goes up. If one part goes down, the other part goes down. Again, it's probably not going to work out to just say, oh, well, temperature is not related. Well, we had to find the new temperature and figure out what that turned into. So yeah, I'd say temperature was definitely important. Okay, then last little group. So these last few go together. We are going to, looks like we're going to minimize everything. So 100 Kelvin, let's grow the graph, have the full isotherm here. Minimum temperature, minimum volume, we get 100 kPa. Okay, and then we're going to increase temperature and increase volume, which seems like that's what number 7 was talking about. But let's pay a little more attention here. So when we increase the temperature, we're going from 100 Kelvin to 300 Kelvin, so that's triple. But then we're going from 1 liter to 6 liters, so that's a lot more than triple. So pay attention that those are moving at different rates. Okay, so let's find this new pressure. 300 Kelvin. And then kind of get the isotherm for free this time because we had to run through the full range of volumes. Well, what's that pressure turn out to be? Yeah, we got 50 this time. That's less. It wasn't the same. It's less. Okay. So let's reset everything and let's try it again. So bring it down again just to see the graph. And we want to go to 400 Kelvin, so we're increasing the temperature. We want to go to 3 liters, so we are again increasing the volume there. Oh, let's go ahead and do the whole thing. This time the pressure went up, right? We increased them both. You can be careful with that part with the different rates though, right? So we increased them both, and then we got a different pressure. We got 133 this time. So let's think about these two and what we said earlier. If you've got excess volume, if you've got more space, then that means that the molecules are less likely to run into each other because they've got more room before they bounce off of each other in the container. And that ultimately gave us less pressure. Here, the temperature grew by a larger amount. So more temperature means more energy. And so even though we do have an increase in volume, the temperature increased more, so we have extra energy because we've got extra temperature. And that's going to make them zip around, move faster, move more, bounce more, and become more pressure. Okay, so I'm not fully ready to say that it's a random process. So let's look through these and see, what we think is true. So if the volume increases by a greater factor, then the pressure goes up. Well, we saw the opposite of that. Remember, having more space means the molecules are less likely to bump into each other. Pressure should have gone down. So I'm not liking either of the first two yet. Oh, but I do like this part because we talked about that, didn't we? It's a word I used earlier, and I said it might be a hint. If the volume increases proportionally to temperature, then pressure will remain constant. So let's try that, right? If we go up in equal measures, if I've got 100 Kelvin and 1 liter, and I go to 200 Kelvin and 2 liters, did that get us back to the same answer again? 300 Kelvin and 3 liters. Yeah, right? So if we go up by equal measures, then we get the same pressure back again. So yeah, I like that one. Let's check the last one just to make sure. If the temperature increases by a greater factor, pressure will go down. Well, no. Temperature, remember, is energy and relates to how fast those molecules are zipping around on average. So having higher temperature and more motion is going to mean more bouncing, and then should therefore mean more pressure. So yeah, I like the proportional one. All right, and that should do it.